Good morning, everyone. Very good to see you. Thank you for coming. My name is DiPietro. I'm the Vice President of Product Management and Applications at Canon Instrument Company. I've had two jobs in my life. For 35 years at a thermal analysis company and now Canon Instruments. Canon Instruments history goes way back to Penn State. It was started by two professors who improved upon these manual tube viscometers. And little did they know how they would revolutionize kinematic viscosity. Used primarily in petro, but we're going beyond that scope from the 1930s. It's still a private company right outside of State College, right outside of Penn State. But that scope is expanding in many ways, and one of those is polymers. And so that's what I'm going to talk about today. Just by a show of hands, who uses thermal or is at least familiar with thermal analysis? Okay, good, because I wasn't planning on covering the basics. I was not all that familiar, quite frankly, with some of these imaging techniques, and so I'm excited to talk about those, really, and to bring them to you. So it's good that you have that background. There's a partnership between Hitachi, who makes the thermal analyzers, Japanese company, and Canon. It turns out that Hitachi is wildly successful in Asia and now in Europe, but not in the United States. And so they hired us to become their tech support and their commercial operation here in the US. We have about 170 years worth of experience at Canon in thermal analysis. So I think we're uniquely capable of meeting your needs. So please do contact us if you need any help with thermal analysis. But again, my main focus is really, I guess, two words. One is unique and the other one's important. Sometimes there's unique features which are not really important. But I think with this apparatus, it's both unique and important. So I've got two slides on these first 2 points, and then all the time will be on example data, and then we'll sum that up. And it's a small crowd. Feel free to interrupt at any time. I go pretty fast, so I don't mind at all if you chime in with questions. You all know the role of thermal analysis. I mean, this has been going on since the 60s, like when I was born. Probably the first thermal analyzers were commercialized originally by DuPont and then Perkin-Elmer, but others have gotten in the business over the years. And so this is a suite of instrumentation: DSC, TGA, DMA, TMA. You know, the use of these is well known. For most polymer operations, this is one of the staple products. So I won't belabor that. If you have any questions about the use of thermal analysis in any application, by all means, you come and see me. I do want to talk about what RealView is. It's an imaging system. You know, companies like ours, we coin terminology that we think is probably cool, but in the end may be confusing. RealView simply means image capability, image analysis. So when I say RealView, it's image analysis. And in our product line, it's available on DSC, the TGA, and the DMA, not available on the TMA. There's two approaches to this. One is kind of more of a macro thing to look at changes in size and color. I'm going to show you a lot of examples about this. And then kind of a higher resolution and an approach where we polarize the light to get a lot more useful information on a smaller scale to be able to look at structure. I'm assuming you could all hear me okay, but if not, just shout out. So, you know, basically you have access to the DSC calorimeter cell, and in this case, the TGA cell via viewing ports. In the case of TGA, you have a quartz furnace. In the case of the DSC, you have a quartz lid. Same thing with DMA. This is a picture of a DMA with the camera attached to the front of it. Here are the cameras attached to the DSC and the STA. So that's the overall general picture. The balance of the TJ is here. The sample platforms and the oven are here. Okay. So to start out with an example, a lot of these slides are confusing, so bear with me. I'm going to take my time to go through it. Cellulose nanocrystals have a lot of benefits, and so they're often used as filler materials, and they can be filled at different loadings. And so what you see here is the TGA curve, simply looking at the filler coming off and then the polymer. Okay, so the filler in 10, 20, and 30% loading. So we have that, and then what we're trying to do is to understand really what's happening in this case to the CNC. The CNC, chief among the properties are its biodegradability. It's environmentally friendly. But as such, it's maybe not a great kind of, it doesn't have great heat resistance. Okay, so it's yellowing. So we can see at different temperatures, I should say at different loadings, at different temperatures, kind of how yellow it's getting. The eye can't really detect if something is yellow per se, but the machine can. So in the camera, you have this color filter array, which is kind of like a mosaic, very small filters on top of the pixels. And so when you think of the image detector on the camera, that can put out a signal, and it does. So in this case, it's on a scale of intensity, which is L. You have this scale called A, which is green-red scale, and then you have a scale called B, which is blue-yellow. Now, people in the color industry know this better than I, that's for sure, but these are common kinds of ways to look at color. And what's not showing here on this axis is the intensity. It kind of complicated it, so we didn't include it. But what is being shown here in red is the yellow scale. So a positive B means that we have some yellowing. Now, it's noteworthy that there's really no, at least on this TGA scale, no detectable stability issues, but you certainly see yellowing going on. So the ability to quantify what yellow means, I think, is very valuable, because there's all kinds of cosmetic type applications and real world examples where it would be absolutely taboo for the sample to be yellow. But again, by the human eye, it can't really be detected. That's the noteworthy things about this example. This happens to be the 10% scan, 10% loading is what we're looking at here. All right, so again, before any discernible weight change, there is certainly a color change. So in the case of polyethylene, polyethylene is often used in wire and cable. And that's where this sample comes from for that industry. It's actually in sheet form, but chief among the important properties of wire and cable is that it can't just melt. It has to hold its shape, because we can't have the wires shorting out. So what's happening in this example is you have two kind of additives to this polymer. Let me describe the experiment. I'm getting ahead of myself. We're plotting time on the x-axis, so this is going from 0 to about a half hour. And what you don't see is that we ramped up to about 200 degrees. We're just sitting, we ramped up in the presence of nitrogen so as not to degrade anything, and then we switched to oxygen. This is an ASTM method for polyolefins. So they're quite common. I think it's 3598. So it's quite common, and so we're sitting at 200 degrees or whatever this temperature is. It looks maybe it's 225. And so we're plotting weight. Okay, so air is switched over to here, I should say oxygen at time 0. And we're looking at, in the case of DSC, which is this green curve, this green axis, we're looking at the onset of the oxidation induction time. So the deviation from the baseline is the OIT, and we can clearly see that there's a difference between samples A and B. In their OIT, we could see that there's a difference in their weight profile as well. But what you can't really, I think, get your head around is that sample A and B both contain antioxidant, and they contain usually mineral type fillers will fulfill this role of of having a high melt viscosity, okay? So you have varying amounts of each, and in sample A, you see a material which has kind of poor oxidative stability, but very good melt strength or melt stability or dimensional stability. Not the case in sample B. In sample B, you know, there's very little dimensional stability here in the end. This shrinks. That would be not good in this industry. But on the other hand, you see a lot of antioxidants. Now, what I wish the scientist would have done in this case is also plot color. Because again, we could have quantified what yellow or any particular color means. So I think this is fairly important. There's no way to really get at this information, I think, any other way. There may be. In fact, if you can think of ways, please see me after, because I'm not aware of it, all right? There may be good ways to get at this information. This, I think, is a fascinating concept as well. So again, I'm trying to weave the case that this is both unique and important, right? Again, we've all been sold many things that are not really important, but I think I know some of these applications well enough to make the case that these are very important. So this is just looking, for instance, at a small sample. Now, this DSC signal, you can't see it from where you're sitting, but I can tell you this is about 40 microwatts tall. So this is a small peak, okay? If you've been doing DSC a while, you'll know what's big and what's small, but it's certainly detectable in our DSC. But sometimes you run much smaller samples that are not detectable. But what's interesting is we're also plotting the intensity of light in purple. So that's this purple axis. And what this means is when there's a drop, it's getting discolored as it's going through the melt. And it turns out we can process this into the derivative, and we can get a proxy of a melt signal, of a heat signal, via light. Now, it doesn't matter how small the sample is, we will be able to see its light. One of the cameras is very high resolution, certainly on the order of a micron. So we can see these things quite well. So here's an example of that. This is generically called fisheye contamination. So these are either mixing problems or high molecular weight stuff that is kind of stuck and presenting a defect. Very often this is in the film industry. How are we doing on time here, Derek? We're okay. And so, again, it's hard to see from your seat. I apologize. One increment is a ½ milliwatt from here to here. So this green signal is this very small sample. It's this smaller speck, and this is a very, very thin film. I think it's 1 micron. So as you know, to get a signal out of the DSC, you need mass and you need heating rate. Okay, and but you're not afforded that in some cases, especially if you're looking at things like contamination. So you can't really see anything. It's kind of noisy. But what's not noisy is the heat signature. I should say the light signature. We're plotting the derivative of the intensity of light, and we see a peak, which corresponds nicely if we take the actual polymer, the contaminant, and run it as a separate sample. So now we have a big piece of sample, and we can kind of see that the light is a very nice proxy for a sample that you could not otherwise see by DSC. All right? This is a sample. Polyvinylidene fluoride has a lot of interesting properties. One of them is it has piezoelectric properties. This is a piece of PVDF coated on a silicon wafer. Now, I don't know if this is an actuator or some kind of a sensor, but it could be. Customer didn't tell us. But what we can do is when we crystallize this from the melt, so you can't see it, and I can't see it either because I don't have my glasses on, what the temperature is here. But we're in the melt, and we're going to cool the sample. Okay, so I'm just going to simply play a video and let you see the result of that. At some point, you're going to see this green line get dark, which is where we are in the temperature scan. And we're just about to hit the crystallization now. And you'll see on the perimeter of the sample, which is probably running a little bit cooler, the crystallation of the sample. Okay, now, one thing I forgot to mention is each data point has an image. Each data point, we can put a scale on there as well. And so I think this is absolutely fascinating. When we zoom in on this and we look at the effect of cooling, of process history, we can see when we cool very fast and we zoom in, it seems like we get a lot of nucleation sites, okay, which kind of makes sense. But there's not enough time for crystal growth. And as we go to slower and slower heating rates, we get less nucleation, but really nice large crystals. Now, again, I think this is profound. There's all different types of crystal structures. This camera is sensitive enough to look at things like spherulites and more fibrous type crystals. When you get into, you know, lamella type crystals, if they fold enough on each other, we could see it. But certainly we could observe, and again, we could put a scale on here and quantify the size, the shape, the orientation, and kind of the density of these crystal sites. I think that's fascinating. You know, the thermal data is one thing, but the structural data is very interesting. This is only permissible by virtue of the polarization and the magnification that we have, the resolution of the camera. Okay? This is a simple experiment of polyether ether ketone, where we're doing a DMA test, and at some point here you'll see the test. We're plotting modulus, tan delta is in blue. This is how much energy it dissipates. And when it goes through kind of the peak, so it's dissipating energy, but now it's the modulus in blue, I should say. I'm sorry, the modulus, yeah, the tan delta is in blue. So the tan delta, there's a rise in tan delta. The sample became crystalline. I don't know if you observed that, but it was more translucent. When we go through the TG, there's enough molecular mobility to crystallize. It became opaque, and then it started to melt again. So that's an example of DMA. Quite frankly, I would say probably the DMA, the more importance there is artifact related. I think there's more information on DSC and TGA, would be my guess. Okay. I think I have just two more examples, and we'll be done. So this is to keep food dry. Hygroscopicity is very important in picking up moisture in foods, crackers, things of this sort, chips. And so this is a microtome sample, so we're looking down. If I had drawn the stripe, it would be here. This is a multi-component composite film, and we use a microtome to get it in a 10-micron thick sample, and we put it flat in the pan. Well, the problem is there's not enough sample here for DSC, okay? When we run this on DSC, we get this green curve. We get nothing. You put nothing in, you get nothing out. So putting a tiny film is the equivalent of putting nothing in your DSC. But what you get very nice is the intensity of the light. That's in purple. That's the derivative of the intensity. And not only could we kind of quantify what the polymer is because we know where it's melting, but when you look at this video, it's going to kick in right about here. And what's going to melt right now in this melting area, you'll see this turn color in the middle. Okay, right about now. So we know that the position of that component, whatever it was, well, we know it's melting around polyethylene. And we know that when we get up here in temperature, we're going to see these two other kind of the bread of the sandwich, so to speak. This is going to melt. This will change darker. and we will be able to identify this as polypropylene. So those are some examples. I have others. I respect and honor your time, so I'm going to stop there. And just to summarize maybe about a couple of things, and I'll leave it at that. I do have these last examples if you want to see them. I did not rehearse the timing of this, so I wasn't quite sure. Let me just make this bigger so you can see it. So again, profound, important, and unique. The ability to quantify color. I think it's very important. The ability to qualify whether or not your mineral filler is actually working. Samples are often so small you can't produce any heat signal, but you will produce a light signal. To look at the effect of processing on things like nucleation and growth of crystals, the ability to reverse engineer things, look at their location in the composite. We didn't talk using DSC as a heating microscope or look at polymorphism, but certainly if anyone's in the farm industry and want to talk about that. Listen, it's kind of you to come and spend your time here. I can't thank you enough. If you want to learn more, you see me now. We're in booth 1316. You could contact us. Thank you very much for your time. I appreciate it.